This is the wave maximum velocity. This is V1. This will be instantaneous rest. This will have maximum displacement. Then okay, let's assume that this will be instantaneous rest. Okay, I agree this one. Now the again a layer may be like this. Okay, fine. So a given layer what pen will execute SHM about its mean position. This is, what is this particular point? Mean position of I will pull it down because I have to. We'll discuss in fresh page. Okay, no, you have things very clear in front of you. What is this gray color that I shaded? It's a layer. So in what direction the sound wave is propagating? The sound wave is propagating towards right. Let's assume. Now, where the layer will have maximum kinetic energy? All of you, IR, okay, understood. What is IR? Instantaneous rest or left extreme, you can call. And what is Y? Y will measure like this. Am I right? We'll measure Y from the mean position. Okay, now we have everything. Okay, now I'm asking you as students one best question. Where the kinetic energy will be maximum? Anybody wants to answer? Where the kinetic energy should be? At mean position, naturally, because the layers are executing SHM. Where potential energy should be maximum? At extreme, potential energy maximum at extreme. No, potential energy, kinetic energy, both will be maximum at mean position, and both will be zero at extreme. Sir, how it is possible? See, like, what should happen to the energy? The energy should propagate, no? Potential energy, kinetic energy, both are maximum. As it moves, both will decrease, and extreme point, what will happen? Will become zero. Where do this energy go? Given to the next layer. The wave energy should propagate, no? The energy should propagate here. So therefore, the energy will be given to the next layer. So therefore, what we can write it as like a U max, K max. And what about here? U will be 0, K will be 0. Similarly, U equal to 0, K equal to 0. Got the idea? This one. Next again, what about, oh sir, what about this one? U will be non-zero, K will be non-zero. If a layer moves from mean to extreme, potential energy, kinetic energy, both will decrease. So what are the important conclusions here? If a layer, just will write it, the layer will have maximum kinetic energy and potential energy at mean position. Next again, the layer will not have zero potential energy and kinetic energy at extreme. Okay, got this one. Both potential energy, kinetic energy will be maximum at mean position, and at extreme will be zero. Where do that energy of the layer gone? Given to the next layer. So in this way, the flow of energy will occur in the direction of wave propagation. Naturally, because it's executing SHM, again, the strain here will be maximum. I'll later on show the dy by dx will be maximum at mean position. I'll show later on. Because potential energy depends on what? The strain. And the strain depends on what? Dy by dx. I can show that at mean position only, the slope will be maximum. Okay, got this. Okay, now we'll get first expression for the power. So now the same energy density is equal to the same formula what we had is equal to rho omega square a square by 2. What is rho? Rho is the density of the medium. Omega is the angular frequency of the sound wave. And a is the amplitude. This is what the energy density. Then what is the expression for power? Power should be equal to rho omega square a square s speed of sound wave by 2. How it returns due to pressure difference, I'll explain graphically. Time being, you just accept this at 10. Okay, this is the expression for power. Rho omega square a square s into v. Okay, now we'll define the intensity. So how you define intensity? Power flowing per unit area. So this will become rho omega square a square vw by 2. This is the expression for intensity of sound wave. Speed of a sound wave, VW, not mu, rho. Rho is there. Energy density, what you write? Energy is equal to energy density into volume. So volume is what? S into delta x. Delta x by delta t will be this one. I think it's correct. Please do accept. You have forgotten formula. Please do accept. Okay, this is the expression for intensity. Okay, now let me go for some. I want the pressure amplitude, displacement amplitude. So if you can recollect, some formulas is what we have. No, what are the formulas we know? Like a VW equal to omega by k. I want in terms of pressure amplitude. What I brought is in terms of displacement amplitude. So let me express this. I have the total answer in terms of pressure amplitude. Any formulas I have to adjust here? What are other formulas? Speed of the wave equal to B by rho. And next, the pressure amplitude is equal to BAK. What is a displacement amplitude? So what is this expression for intensity in terms of displacement amplitude? In terms of pressure amplitude, I want. So therefore, shall I go for any modification? So expression for intensity, no, this should be equal to. So I want the pressure amplitude. So in place of A, shall I bring delta PM? Or we can replace, no, rho equal to I want delta PM in the equation. That has to be omega square. First, let me write rho. Omega square, what we can write it as K VW whole square A square VW by 2. VW whole square can be written as B by rho. Rho K square A square VW by 2. So this will become rho K square A square VW by 2. VW square, I can write it as B by rho. So one rho get cancels. So this will become B A square K square BW by 2. Let me adjust one B here. So B square A square K square by 2 BW by B. What is BAK whole square? Should be delta PM. What is this delta PM? It is called as any name for that? There are two things are there for you. What is delta PM? Pressure amplitude. What is A called as displacement amplitude? You can also bring density amplitude also, rho AK. Of course, may not be very important, possibility of asking. So you have come across the two formulas. The intensity of sound wave becomes very important than energy density, because I'll be more bothered about this intensity. So two formulas you have to remember: intensity of sound wave in terms of displacement amplitude, intensity of sound wave in terms of pressure amplitude. So these are the formulas. So like this will happen. So now you can ask question from where this you brought it. So the same equation, y equal to a sine omega t minus k, the same equation is there. No, because of that I'm able to directly start this one, or else you have to derive. Let the kinetic energy of small elemental area be dk. If you derive again, we'll end up with same equation. So as there's also a traveling wave, so it also satisfies wave equation. So I'll take help of the same formulas here. So what is this? What we have brought it? Intensity of sound wave in terms of pressure amplitude. The intensity of sound wave in terms of displacement amplitude. I'll just highlight this so that you can notice. Or these formulas, do remember, you have plenty of numericals based on this one. Okay, let's study something. I think what all you know now. Okay, just some rough idea. Means like we have not understood anything. You're writing some equations. Okay, we are accepting it. You are saying potential is both maximum at mean portion, at extreme it will be zero, you're telling. Okay, let me explain through mathematically all the things here. So let me take the equation y equal to the displacement wave equation. Let me